Welcome DC Circuit students. In this mini lecture, I will be showing you the setup for a parallel DC circuit build and measure. And so this is one part of the video series on this. The other parts will include hand calculations and Excel spreadsheet showing results. But for this part, I'm just going to show you how to use your protoboard and hook up your resistors and your voltage source in a way that will make your measurements easy. So for this experiment, we're using a 9-volt true DC source. Remember, electrochemical sources are true DC. So we know that we have that limitation that we will have a maximum of 9 volts as our source voltage. So that will basically set the stage for what we will want to use for resistance to make sure that we don't have currents through any one of our resistors that exceeds its power capabilities. So in this case, we've already done some preliminary calculations to choose our resistor sizes. And so I'm just going to show you how I would hook up the circuit. So I'm going to start by verifying my resistor values. As you know, resistors come with a tolerance. And so the nominal resistance is not necessarily what you're going to get. These resistors all have plus or minus 5 or plus or minus 10, so it will be somewhat close. But we're going to see what they really are. So for that, I'm going to kind of scan back and show my multimeter. I have it set to ohms. So I'm going to go ahead and I'm just going to jot down what my real resistances are. So as you know, you can get the nominal resistance of each of these by looking at the color bands, which are in some cases a little bit difficult to see, and that's another good reason to go ahead and test them. So we're going to start with this first one. So this is a nominal 2700 ohm or 2.7K, but in reality it is 2686 ohms. So when we do our calculations, we're just going to go ahead and include our actuals. And I'm just going to go ahead and test all of them with my multimeter. If you're doing approximate calculations, this is less important, but if we can, we might as well. So our next one is, it's a nominal 2200 or 2.2K. In actuality, it's 2,150 ohms. And I am basically lining these up on the paper so I don't have to look them up again or get a magnifier. Sometimes a magnifier helps you see the color bands a little bit easier. And so my last one, I'm just measuring these individually. Remember, don't touch the leads with your fingers or you'll be measuring yourself in parallel with the resistor, which you probably don't want to do. So this last one is a nominal 3.9 kilo ohm, and in actuality it's 3,893 ohms. So we're just jotting those down, and those are of course at room temperature. These all will vary a little with temperature, but in most cases resistors have a limit in how much they will vary. So now we're going to kind of move our multimeter to the side, and now we're going to think about the best way to line up our circuit. Let's focus on our protoboard so that we can make our parallel connections. So I think the first thing that we need to do is set ourselves up to use the power rails. So when we hook our battery up, our DC source, we can access it fairly easily. So we're going to go ahead and supply at least one set of circuit build rows, like in this case it's row 62, and connect it to one power rail. And then we'll go up a ways. Remember, everything on all of the power rail holes along this one part of our protoboard are all continuous. So we can use that to our advantage to make it easier to build. And we can go ahead and make our other power rail connection up here at row 44. Oop. Okay. So now all I have to do is hook my battery in anywhere on the power rails, and that'll make it easier to connect that, because I'll be doing that with some jumper cables, because I have stranded wires on my battery connection which do not plug into the protoboard. Do not try. So now all I have to do is take my resistors and go ahead and make a parallel connection. So that means I want basically one end of each resistor to be basically iso potential, or connected to the same potential as the positive rail, and the other all the same potential as the negative rail. So the easiest way to do it would be to have each resistor bridge the same set of holes. So that means I have to bring one of my little rail jumpers over a little bit closer, since I don't want to use additional jumpers. So I'm trying to do this with the least amount of fuss. So I have positive rail connected into this row, and that means I can connect 1, 2, 3, 4 additional components into this one row, row 56, so they're all continuous. And then I have my negative power rail connected into row 62. So I'm going to go ahead and put all of my resistors in parallel. So that means that basically row 62 and row 56 of the circuit build area are only being connected with resistors. So current has to flow through these resistors, and it will flow through all of them at the same time in order to get from one to the other. So this is a parallel combination. So let's zoom in on this a little bit, make it easier to see. So basically I'm going to connect my battery in on somewhere on this blue rail, close to the blue line, and then I'm going to connect it somewhere close to the red line. Now if I want to check to make sure that I've connected this properly, I know from my knowledge of parallel resistors that the equivalent resistance of all three of these in parallel will be somewhat less than the lowest resistor. So I know my lowest resistor is 2100, so if I hook my ohm meter up and I measure what the battery will see, the load of the circuit, the total resistance, I should get something less than 2100. And in fact, if I do that, I will view my meter here. You can see that the meter is saying it's just a little bit under 1K, which is definitely less than 2100. So I know that my circuit is nominally hooked up correctly in order to give the configuration that I wanted. And given that, again, I have a parallel stranded battery connection, in order to power this circuit, I will connect my little power rail leads using a alligator jumper. Not necessarily good practice for a more permanent circuit, but if you don't have solid wire to go directly into your protoboard, this is a great alternative to actually make your connections. And I happen to have a yellow wire for both. So when I make this final connection, I will be making a continuous path from my 9-volt source through my 3 parallel connected resistors and out. So now I'm set up at this point to energize the circuit, and of course I could measure the voltage drop over any one or all 3 of the resistors, but I know that because they're all in parallel, that they will effectively be the voltage drop over the whole circuit, which will be about 9 volts. A little bit less because electrochemical sources sag a little bit. This battery has some internal resistance, so it will supply somewhat less than 9 volts once we have current flowing. And so the task for our measurement will actually be to configure the meter in series with first the whole circuit. So we'll put our meter in series right here where we've broken the circuit, and then we'll go back and we'll put our meter in series with each of the resistors. We'll have to reconfigure our circuit a little bit to verify the current going through each branch. And then we can discuss meter measurement capabilities, because one of the things I'm sure you all know from having read the specs on your meters is that multimeters are really good at measuring voltage but not so good at measuring current. So typically meters will be limited to plus or minus about 1 milliamp. This particular meter will measure a little bit to a little bit better resolution, but in any case we'll have to compare that to what our calculated currents are through each branch in total, just to see how much we'll be able to measure. So at this point we've completed our circuit build. We know how to measure the current by putting our meter in series with the battery and the whole circuit. And we've also measured the actual resistance as opposed to the nominal resistance of each of our 3 parallel resistors. So now we're ready to take a break and go back to our calculation sheets and start calculating our total resistance, our total equivalent resistance, and then pre-calculating, estimating our total circuit current and our current in each branch. And then we'll compare that to what our meter can measure, and then we'll come back and in a subsequent video we'll go ahead and make those measurements. So see you for that one.